welcome to our physical sciences session. My name is Temba. Today we are focusing our attention on exploring electricity, which is a concept that comes from way back, from our earlier grades. So today we'll look at, various aspects of the Ohm's Law. That's ultimately what we want to achieve at the end of this session. But also leading to that, there are some concepts in as far as, series and parallel circuits. We'll also look at the relationships that exist, between potential difference in current, and ultimately decide whether a particular type of a material is, a ohmic or a non-ohmic conductor. Right. So without any waste of time, let's look at the concept map involved. Okay. So we are going to look at concepts or quantities such as current. All right. Which has to do with the rate of flow of charge. Okay, that's what electricity is all about. And then potential difference, which is voltage, that has a lot to do with energy and work done in moving the charges, which ultimately become the current. And then also electrical resistance, is one of the aspects that we want to discuss today. However, we remember that there are two types of connections in a circuit. It's either parallel or series. So, and ultimately would want to look at the Ohm's Law, in terms of its application, and decide whether a conductor actually obeys Ohm's Law, if it's an ohmic conductor or a non-ohmic conductor. All right. But before we look at the Ohm's Law, this is the thought which is, is going to guide our discussion today. The thought says, have you ever thought about what happens to current and potential difference? Okay, that's your voltage in a series and parallel circuit. So we're thinking about the relationship that exists between potential difference and current in one of the two, in both circuits. It's either series or parallel. And then also the other thought, what relationship exists between current and voltage through a resistor. Okay, this one is about a resistor. And then again, same question, but it has to do with the light bulb. It says the relationship between voltage and current through a light bulb. So these are the thinking exercises that are going to guide our session for today, right? Okay, now terminology, which is a very, very important aspect of our subject, because remember, definitions, it has to do with the language as well, okay? So remember, we use the examination guidelines as our source of reference in as far as definitions are concerned. What is acceptable, okay? Remember the keywords that must also be used in the correct context. Okay, so what are some of the terms that we are going to discuss, or that we already know by now? We know something about EMF, which has to do with the maximum, okay? Amount of energy, okay, of energy that a battery, okay, can dissipate, okay, can dissipate per coulomb of charge, right, per coulomb of charge. So the coulomb is the SI unit of charge, okay? Right. So there's a difference again between EMF and EMF reading. So the EMF reading, as we know it, is the reading across of the voltmeter connected across the battery, okay? When there's no current flow, we will talk about that. And then we talk about current as the rate of flow of charge, all right? Okay. Okay, that's the rate of flow of charge, just to remind ourselves. And then potential difference has to do with work done per coulomb of charge, okay? That's work done, okay, per coulomb of charge. And remember, when work is done, energy is transformed from one form to the other, because we know that energy cannot be created or destroyed, but it can be converted from one form to the other. So this is work done per coulomb of charge. That's voltage. While resistance is the ratio of voltage to current, okay? Just to sum it up. And then we'll talk about the Ohm's Law, because we want to arrive or discover what the Ohm's Law is all about, okay? Right, so some of the key words are ohmic conductors, non-ohmic conductors, potential difference in terms of terminal potential difference, okay? And then independent variables, because we'll do some bit of scientific inquiry in terms of verifying some of the facts that we already know leading to the Ohm's law, okay? Right, now just to break it down once again, we're saying current, the symbol is I. So the quantity is current, then the symbol is capital letter I. The capital letter I actually stands for current intensity, which has to do with how many coulombs of charge pass through a point in a second, through a conductor per unit time. And when we say per unit time, we're talking about a second. So current is defined as the rate of flow of charge, okay? So this is the concept of current, all right? Which says mathematically, current is charge over time, and then the time is in second. So an ampere of current is actually when 1 coulomb of charge passes through a point per second. So if, for argument's sake, we're saying we have a reading of 3 amperes, what does this mean? It means that there's 3 coulombs of charge passing through a point per second. Okay, so correspondingly, the greater the amount of charge passing through a point, there is greater current. Okay, so an ammeter is a device which has got low resistance. What do we mean when we say it's a low resistance device or an instrument? It means that all the current will pass through the ammeter, and we're saying that the ammeter, does not offer any resistance to the flow of charge, right? So it is always connected in series. So when something is connected in series, we are saying it is connected at a point, all right? Okay, it is connected at a point. This is what we mean. Say we've got a conductor, and then there is our ammeter, right? So our ammeter is our device, current is the quantity, while the ampere is the unit, okay? Right. Then let's look at potential difference, which we sometimes refer to as voltage. So take note, the symbol for potential difference, of which potential difference is actually the quantity. V is the symbol, okay? At the same time, V is also the unit in terms of, the shortened version of volt is actually the unit. So we've got voltage, okay, just to get that out of the way, which is V as the quantity, all right? And then we've got the symbol, okay? The symbol, which is also a V, okay, voltage, as well as the unit. So the unit is also V, but the symbol is V, and then the unit, okay, is volt, okay? The unit is volt, which is also in uppercase or capital letter V. So a voltmeter offers high resistance. What does that mean? No current flows through the voltmeter, okay? And then it is always connected between 2 points, which is in parallel. That's what it exactly means. So if we're saying that voltage is the work done, so when we talk about work done, we talk about energy transformation, okay? So, when you talk about that work is done in moving charges between 2 points, in other words, it transforms one form of energy into electrical energy for every coulomb of charge. So we can talk of energy transformation, right? Which means from one form to the other, okay? So these are some of the concepts that we need to remind ourselves, okay? So if we're saying that, for example, potential difference across a resistor is 1 volt, what does it mean? It means that every charge is offered a joule of energy, okay? Or 1 joule of work is done in moving a coulomb of charge between any 2 points. So the issue of language is very, very important there, okay? Now, the EMF is something that is very important in terms of, of a simple circuit. The battery offers or provides the EMF, which is the maximum amount of energy, right, per coulomb of charge. So EMF is some form of voltage, if you think of it, because also it's measured in volt. And if we connect a voltmeter across the battery, when there is no current flowing, that reading is actually the EMF. So take note, this is the definition of EMF. Okay, this is the definition, while this one is the reading, right? So we need to distinguish between the two. What's the difference? The definition, it's what the quantity is, and then the reading is the measurement of that quantity. So in an open circuit, when there is no current flowing in the circuit, the reading of the voltmeter that's connected across the source, it gives us an indication of the EMF, okay? But the moment we close the switch, current starts to flow in the circuit. When that happens, the same voltmeter connected across the battery actually gives us an indication of what is called the terminal potential difference, okay? Right. Now, so the external terminal potential difference is measured by a voltmeter connected across, always across the battery when current passes through the battery. So this slide actually talks to the difference between, you know, EMF and terminal potential difference, okay? Right, so these are the concepts that we need to remind ourselves of each time we talk about electrical circuits, right? Okay, now let's look at resistance, okay? Electrical resistance, the symbol is R, okay? There's something interesting about resistance that we often fall into that trap. You know, if we talk of a resistor, we talk of a device, okay? So resistor is a device, okay? So a resistor is a device, okay? And it can be a light bulb, it can be, you know, anything that transforms electrical energy to other form, okay? It can be a heater, it can be a speaker, anything that transforms or changes electrical energy into another form, it's a resistor. And then resistance is the quantity, right? So resistance is the quantity, okay? And then the ohm is the unit, okay? So what is resistance? Generally is the opposition a conductor offers to current, okay? So in a resistor, the resistance is dependent on the type of or nature of conductor or material that makes up that conductor. Some materials, they offer high resistance. Some they offer, some conductors, they offer low resistance. Those that offer high resistance actually have got greater opposition to the current flow, okay? While those that offer lesser resistance, by comparison, they offer lesser opposition, okay? So resistance can be calculated or determined in terms of the ratio of voltage and current, you know, through a device or through a component in a circuit, all right? Okay, so that's about the resistance. So in other words, if we have 1 ohm, for argument's sake, what do we mean? Okay, that's the symbol for ohm. What we mean that we've got 1 volt per ampere, okay, because that's the ratio of voltage and current, right? Okay, so these are some of the very important, you know, concepts or, you know, ideas that we need to understand before we even explore anything that has to do with the Ohm's Law, right? Having said that, let's take a short breather. When we come back, we'll look at a different scenario where we talk about the relationship between potential difference and current in one of the 2 circuits, the first one being a series circuit, while the second one has to do with the parallel circuit. Let's take a short breather for now. Welcome back to our second segment. We're still looking at you know, exploring electricity, but now we want to focus our attention on the series parallel, you know, circuit in terms of your voltage, your current, and resistance. How do each one of those, you know, relate to each other? So the big questions that we are asking ourselves on this one is that, okay, there are 2 types of circuits in terms of connection. We've got a parallel as well as a series, but we want to see how that affects the current voltage relationship in each one of those types of circuits, okay? Right, so the idea says predict what happens to current and voltage in a series circuit, that's one, and then secondly, we'll look at the parallel circuit as well, okay? Right, here we've got resistors in series, okay? Now, this is just a snippet from, the FET simulation, which actually, simulates what happens in an actual circuit. Now, if you look at the layout here, let's say for argument's sake, we've got resistor 1 and resistor 2. The description of the connection of these two resistors is that they are connected in series. And what does that mean? It says that there is only one path of current for current to actually flow. So the amount of current that passes through R1 equals to the amount of current that passes through R2. So what are we saying? We are saying the total current passes through R1 as well as R2. So the reading, for example, in this case of 2 amperes is the main current or the total current of 2 amperes, right? So this is what it means. It means that R1 gets 2 amperes while R2 gets 2 amperes. Why is it so? Because all the current passes through every point, because we've got only one path for current to actually flow, right? So this says to us that, okay, in a series circuit, current actually remains constant. So the total current is equals to the current that passes through R1. We can call that current 1, and then which is also equal to the current that passes through resistor 2. So we can also describe that in terms of notation as I2. So all the current in this circuit remains constant in a series. So we are saying, in short, current remains constant, right? It remains constant. Okay, so there is the same amount of current through every point in that circuit. But what about potential difference or voltage? Voltage is actually divided. Say if, for argument's sake, we've got this circuit here over here, and we know that, let's say, the total voltage is, let's say, 9 volts, right? Okay, and then this is connected across the battery. So that's our terminal potential difference. And then we've got R1 as well as R2, right? If we were to use symbols, right? So what do we have here? We are saying that the 9 volts is split between this V1 and this V2. So in other words, we are saying that the voltage across R1 plus the voltage across R2 must give us the total voltage. So V total in this case is equals to 9 volts. But this 9 volts is it comes from V1 plus V2, okay, which is exactly that. Then what do we mean here? We are saying that voltage is divided, okay? So in other words, you describe a series circuit as a potential divider, okay? But then when it comes to the total resistance, now there are 2 resistors that are connected in series, okay? Now, if that happens, if that is the case, we are saying the total resistance in this circuit is R1 plus R2, okay? But if there were more than 2 resistors, would have R total, as long as the series circuit is equals to R1 plus R2 plus whatever until plus Rn for n resistors that are connected in series. So this is what we need to understand about a typical series circuit, okay? Right. Now, if we go to a parallel circuit, all right? So that's the battery there, okay? And the 2 resistors, still the same resistors, R1 and R2, okay? You'd realize that these 2 resistors are actually connected in parallel. And what do we mean by that? We are saying that when current, part of the total current goes to R1 and some of it goes to R2. So that's your current 1 and then that's your current 2. So if you add the current that is split, which is current 1 plus current 2, it must give us the total current. So in other words, in a series, we are saying that the total current is equals to current 1 plus current 2 in this case, because we only have 2 resistors connected in parallel, all right? So when this happens, we would say, okay, current is split because there is more than one path for current to flow. But there's something that's very interesting about a parallel circuit that we need to remember. If we say, for argument's sake, this is V1, okay, and then this is V2, right? So there's something that we also need to check is that the voltage, as long as it's a parallel combination, must remain constant. Let's say this is the V total, which is the terminal potential difference. So we would have a case where we say V total is equals to V1 plus V2, all right? Now, is equal to, not plus, okay? So we're saying it's constant. So if it's constant, it means the amount of voltage across any point in that circuit remains constant, which takes us to the next slide where we actually appreciate that current is divided, okay? So this is what we are saying in as far as the parallel circuit, that current is actually divided, okay? So we would also describe a parallel circuit as a current divider. Current is divided, okay? So that's the main thing about a parallel circuit, while voltage remains constant, okay? As you'd have realized that the voltage across the source equals the voltage across the resistor 1 as well as resistor 2. So we are saying that voltage remains constant, okay? This is what we are saying in short. Right? But then when it comes to resistance of a parallel circuit, you'd remember that you can actually determine if there are two resistors in parallel, you can use the product over sum formula, which says total resistance in parallel is equals to product, which is R1, R2, over the sum, which is R1 plus R2. But this is only applicable for two resistors connected in parallel. However, there can be even more than two, resistors connected in parallel. So it takes us back to 1 over R parallel, which is the total resistance, is equals to 1 over R1 plus 1 over R2, okay, plus whatever in between, okay, 1 over Rn. So this is applicable for n resistors that are connected in parallel. Be mindful of that. So this is the gist or the main idea in as far as the parallel circuit is concerned, okay? Now we focus our attention on the relationship between potential difference across a resistor, okay, and the current flowing through it. Okay, this is just a snippet of a FET, setup of apparatus, just that is going to help us to actually obtain the data. You'd realize that there's a battery there, and then a one resistor that's connected at a point in series, and then that current is actually the total current, okay? So we will actually go to a simulation now and just try and get some values, in as far as the relationship between potential difference in current through a resistor, okay? So for our simulation, this is what we have now, all right? Okay. Now, this is a simple circuit that has been actually connected on a FET simulation. So this is the actual one, okay? So if we say, for argument's sake, we start with, let's say, 1.5 volts across the battery, okay? This is the voltage across the resistor, and that's the corresponding current reading. So that current is actually the total current. So if we go back to our table, okay, of results, we are having a voltage across the battery. The voltage is 1.5. Across that, even across the resistor is 1.5, because that's the total voltage with a current of 0.75. So if we go back to our table, we have there's one cell there. One cell is 1.5 in this case. So our potential difference is 1.5 volts, and then the current was 0.75 amperes, all right? Now, let's go back to the simulation, okay? What if we use two cells? It's just as good as doubling the voltage of this cell, okay, to 3 volts, okay? These 3 volts, you can see the current is now 1.5 amperes, okay? Let's go back to our table, okay? So for 3.0, which corresponds to two 1.5 volt cells, it gives us 1.50 amperes, okay? we can all immediately pick up the trend that as we get the potential difference greater and greater across the resistor, so does the current. Okay, let's make it 3 times as big, which is corresponding to 3 cells. So this is going to be 4.5, which is 4.5. It corresponds to 2.25 amperes of current. Okay, let's populate our table very quickly. So this is 4.5 volts. Okay, that's the voltage that was recorded. The corresponding current is 2.25 amperes. Now, there is something that we also need to check here. Okay, the ratio of potential difference to current. Okay, so if you say V over I, in this case, for one cell, you'd have V over I, which is equals to, okay, our voltage is 1.5, okay, 1.5 divided by our current, 0.75. This actually gives us 2, okay? So we've got 2 there. The same goes for that, 3 versus 1.5, and 4.5 versus 2.25. So you see that the ratio of potential difference to current remains the same. So if we were to tabulate these results and plot a graph, it will actually give us an indication of the relationship that exists between potential difference and current through a resistor, okay? And then that takes us to our graph, okay? Now, this is the pattern that we got. As we increase the voltage or the current, the voltage also increased. So there is a linear relationship that exists between those two. Now, if we go back again to the questions, it says, if we plot a graph, okay, we got a linear relationship. There is a linear relationship, okay? So there is a linear relationship. That's the main thing that we wanted to establish in as far as that relationship, okay? So the graph suggests that the current and potential difference are actually directly proportional, okay? So if we go back to that, so we are saying current and, okay, potential difference directly proportional, okay? They're directly proportional. And then what does the gradient represent in this case? The gradient actually represents the resistance, because the resistance is actually the ratio of voltage to current, okay? It represents the resistance of the resistor concerned, okay? Right, and then in conclusion, we are saying that the potential difference across a resistor is directly proportional to current passing through it, provided the temperature remains constant. Now that's how we actually arrive at the Ohm's law, right? Okay, so that was it as far as this segment is concerned. In the next third and final segment, we'll look at a scenario where instead of a resistor, we use a light bulb. Let's take a short break for now. Welcome back to the third and final segment of our session. We are still exploring electricity. Now our focus of our attention now is on actually, we want to look at, what happens to the relationship between, potential difference and current. Now, instead of a resistor, we would actually use a light bulb and see whether at the end of the day, does that same linear relationship exist, and maybe decide in terms of why is it the way that we actually get the results or the data, right? Now, this is what we are saying. We have managed to look at both series and parallel circuit, and we know what is happening in terms of the voltage, the current, as well as resistance. But now we are exploring the Ohm's law using, ohmic as well as non-ohmic conductors, and also try to understand whether the same relationship holds between current and voltage for an ohmic conductor as it would do, say, for argument's sake, a non-ohmic conductor. And then we can, at some point, arrive at some conclusions or logical deductions, that is, okay? Right, so here's a scenario here. The question, the big question, which is the third question for our session for today, it says, what is the relationship between potential difference across a light bulb? Now, let's try and break this down. Across a light bulb and current flowing through it, let's understand there are different types of conductors. A resistor on its own is a conductor which offers a certain opposition to current flow, okay? But also a light bulb is also a conductor. However, the resistance of the light bulb may not necessarily be the same as that of what you call, the resistor. So we're trying to establish that in the place of a resistor, we place a light bulb and try and explore the relationship that exists between the potential difference across that resistor as well as the current that passes through it, okay? So it's a simple circuit, with one cell that is connected at a point, and then we've got only one light bulb there. Okay, this is the kind of setup, just to give you an idea that, right, this is actually the device that offers resistance. So we are mainly interested in the potential difference across this light bulb as well as the amount of current that passes through it. The reason why we are saying across is because the voltmeter will be connected between 2 points, which is across, that is in parallel. So in other words, we are measuring the amount of work done in moving a coulomb of charge across that light bulb, while the current that passes through the light bulb is actually the current that will pass through at any point. So we've connected the ammeter at a different point, but whatever current is registered by this ammeter at this point will actually be an indication of the current that passes through the light bulb, because this is typically a series circuit, right? Okay, so having said that, okay, suppose we were to set up that circuit, okay, and try and investigate, the amount of put the work done per coulomb of charge versus the current, and then subsequently determine the ratio of voltage and current. Okay, because we want to explore that relationship, okay, let's say the data had already been obtained for us, okay? These are the values. The 1.5 corresponds to 0.75. So if we go back to our table, we're trying to work backwards. 1.5 corresponds to 0.75 amperes, right? And then if we go back to that graph, just to extract the data, and then the 3 corresponds to 1.5, okay? 3 corresponds to 1.5. We go back, okay? So if we double the voltage, it's going to be 3. Okay, and then 3 times, which is also a representation of 3 1.5 cells, okay, 1.5 volt cells. This will be 4.5, all right? So we said that the 3 volts goes with, from the graph, it goes with roughly 1.5, okay? So we go to the table, it goes with 1.5, okay? So there is some bit of a trend. However, if we look at the voltage of it's the current of 2.25, it goes with something like what? Because this is 4.5, this is like 5.5, okay? So if we go back to the table, it goes to 5.5. Now, amperes. Now you do realize that what is actually happening, the ratio of voltage to potential difference is not actually the same. Maybe for the first two set of values, there is a proportional increase. But when you look at the third one, actually the pattern is kind of disrupted. And if we go to our calculator just to establish the ratio of current to potential difference to current, these are the values that we have. So we've got 1.5 over divided by 0.75, which gives us, it should give us 2, right? Okay, it should give us 2, okay, right? So if we go back to that, it should give us a 2 here, okay, right? Just a moment. So the ratio for the first set of values, which corresponds to 1 cell of 1.5 volts, is actually 2, okay? What about the second one? 3 corresponding to with 1.5 is also a 2. However, when we do the 4.5 versus 5.5, let's check how that goes in terms of the ratio. So V is 4,5, okay? Is 4,5 divided by 5.5, okay? All right? We get something like what? 0,81 or 0,82, okay? 0,82, right? So if we go back to the table, we would actually realize that it's a value of 0,82, right? So you can immediately tell that no, the pattern is actually not what we expected. So even if we go back to that graph, you'd realize that these points, if we were to extrapolate this graph from the origin, so the linear relationship that we expected or would have anticipated actually does not fall into that. So instead of, we expected the trend to continue. So at some point, the resistance, because we said the gradient actually represents the resistance, which is the ratio of voltage and current. Now, as we increase, the amount of current flowing through it, the potential difference that corresponds to it actually does not fall into what we would have predicted. So there's something very special about the light bulb that I think we can immediately pick up from this. And remember, we said the resistance of a material entirely, of a component, actually depends on the type of material that makes up that component. Some materials, they tend to offer greater electrical resistance, while others they do not. Now, in terms of the Ohm's law, which is what is of interest to us, okay, we're asking ourselves important questions, okay? Now, we can immediately tell that the potential difference across this light bulb, okay, is not directly proportional to the current that's passing through it. That's the long and short of it in terms of the light bulb. But remember, a light bulb as a resistor, not only does it give us light energy, but as it does work, as it transforms electrical energy into light, some of that energy actually is converted to heat. So the temperature of that component does not remain constant. But what did we say about the Ohm's law? We're saying the Ohm's law states that the current and potential difference across a conductor is that they are directly proportional, provided the temperature remains constant. So that condition of temperature remaining constant is actually necessary and sufficient for us to say, yes, indeed, a particular component obeys Ohm's law. If the temperature changes, then it means that conductor is what we would describe as a non-ohmic conductor, right? So because it's not directly proportional, it means it's a non-ohmic conductor, okay? So in summary, what are we saying? The Ohm's law states or gives us that the current flowing through a resistor is directly proportional to the potential difference across the resistor. This is the condition then which says the temperature must remain constant. So what typically an ohmic conductor is that type of a conductor that obeys Ohm's law. The practical example is a nichrome wire. So a nichrome wire obeys Ohm's law. So if the potential difference increases across a nichrome wire, so does the current that flows through it, okay? So hence it is an ohmic conductor. While a non-ohmic conductor does not obey Ohm's law, we've established that by using an example of a light bulb, right? Okay, right. So these are the concepts that we managed to actually look into. So in terms of pre-knowledge, what we already know, we agreed that we must understand what current is all about, okay, as well as voltage as the quantities involved in the Ohm's law. One is an independent variable, one is a dependent variable, depending on how you actually do that. And then we said as long as the resistance is the ratio of voltage to current in any electrical circuit. So if you calculate the gradient of voltage versus current graph, you actually get the resistance, because the Ohm's law actually says to us that V is equals to I times R. Okay, so there's a variation in terms of the subject. We can also talk about the ratio of voltage and current, which is V is equals to R is equals to V over I. Okay. Now we have also said to ourselves that the Ohm's law talks about ohmic as well as non-ohmic conductors. So we'd say that a nichrome wire is a perfect example of an ohmic conductor, because the potential difference in current are directly proportional to each other, and also that temperature remains constant, while a light bulb is a perfect example of a non-ohmic conductor. But remember, with the light bulb, we've already indicated that, while it does work in terms of energy transformation, some of that electrical energy is not, all of it is actually not light. It's not converted to light. Some of it becomes heat energy. As a result, the temperature of a light bulb, as it does work or as it transforms electrical energy to light, is actually converted to other forms. Hence, the temperature does not remain constant. Hence, you think of a light bulb as typically what we would refer to as a non-ohmic conductor. So these are the different concepts that have got to do or lead up to the Ohm's Law, okay? And we understand them because we look at each one of them at a time. But at the end of the day, we need to, try and bring all these pieces together to get the big idea. Hence, we're saying when we explore electricity, our pre-knowledge on the quantities of electricity, that's your current, that's your resistance, that's your potential difference. You need to understand how they fit, because before we even look at their relationship, we need to understand what each one of them is all about, okay? So because of time, this is what we actually wanted to discuss today. We have managed to arrive at the Ohm's Law, and at this point in time, we are able to distinguish between an ohmic conductor versus a non-ohmic conductor based on the Ohm's Law, which states that the potential difference across a resistor is directly proportional to the current that passes through it, provided the temperature remains constant. So the qualifying condition to say that a given type of a resistor is an ohmic is that the temperature must remain constant for that relationship to hold. Then we'll describe that material as an ohmic conductor. Having said that, for myself, Themba Ncube, is cheers and bye-bye for now.